today, which is, I believe, chapter 4, I believe. So it's going to be a lot of fun. It's going to be a lot of fun. And
It's going to be some of the meat and potatoes of amateur radio. So I don't know if that's going to be fun or not, but well, let's give it a try. So when we start off with propagation, well, first of all, let me say I brought a few toys over here at the corner because I didn't know how many people or where everybody sits. I've been out of action for the past 3.5 weeks due to some surgery down here, and so I'm recovered enough that as long as I sit down, I'm going to be fine. So I didn't remember where everybody or how many we had. Plus, fact, it's a nice rainy day. Who the heck wants to get up out of bed, travel? Well, even if it's down the street for some of y'all, but over an hour for me to get here from Williamsburg. Who wants to do that on a rainy day? Not me. So thank you all for showing up. So propagation. Propagation, for those of you into gardening, you're thinking propagating plants and things like that. How is that different than propagation when it comes to radio waves? I think both kind of refer to a growing or getting from one point, a seed, to the next point, which is a nice big tall blooming plant. Where radio waves, we're talking about getting from a radio transmitter to a radio receiver. How does that happen? So that's propagation. That's what we want to spend the first little bit of time talking about. It's a lot of material to cover because somehow I got to get this into antennas also at the end of class. And boy, that is just a lot to cover. Usually with when we do this in Williamsburg, this is a 2-day class, but I got to fit 2 days into a single day here. All right, so we're trying to get from point A to point B. It can propagate in many different ways. Frequency is the one way. The frequency of the wave, I think you've been talking about that here in the last couple of classes. Maybe if I move over here too, I can see my slides. As long as I'm not hiding from the camera over there, that's a new addition. Characteristics of the environment. So, I mean, everything affects a radio wave. The environment around, what's going on outside right now affects propagation on the on the higher frequencies, rather. VHF, UHF, and as technicians, this is important for you all to know. It won't affect HF as much, the high frequency, but you don't have to worry about that until you start studying and get into the general class extra. So yes, radio rain will affect it. The leaves on the trees and flowers and everything coming out now that it's springtime affected too. So that kind of environment. Right here in this room, I got 2 radios right now tuned to the Gloucester repeater, and we can't even hit the Gloucester repeater from inside the building here because of the environment around us. Anyway, so we'll discuss 3 basic ways here that radio waves, particularly UHF and VHF and above, plus HF, how it propagates in 3 different ways. Line of sight, ground wave, and sky waves. And what does that all mean? So on the first slide here, line of sight is more of this bottom one, and I see the camera doesn't pick this up, so sorry about that, folks out in camera land. But on the Earth, we've got 2 radio towers depicted on the far sides of the horizon. As long as that transmission site is just above the horizon, it's got a straight line of sight to the receiver site that's on the opposite side of the horizon. If that were any of those two were lower towers where the horizon gets into the way, it's not going to propagate. It's just not going to reach it. Not on UHF, VHF. The lower HF frequencies, it will, and we'll get to that in a minute. Well, in fact, we can get to it right now. Particularly on the HF thing here, the next propagation, ground wave. Here, the horizon is in the way, but the ground wave, particularly at HF frequencies, travels for a bit of a distance along the ground, the curvature of the Earth. And so if you are over the horizon, depending on conditions, propagation conditions, depending on the power of the transmitter, depending on the sensitivity of the receiver, even though an HF radio is on the opposite side, the receiver will pick it up if the conditions are good. Skywave propagation, that's the third one. Now this is truly HF, the low shortwave frequencies. Anyway, 3 meters, hang on a minute here, 160 meter band all the way up to the 10 meter band. Skywave propagation, it transmits, goes up into the ionosphere. The ionosphere will refract the signal back down towards the Earth. And so that can be over the horizon. And the Earth itself can reflect that signal back up into the ionosphere. And the ionosphere will refract it back down towards Earth. Now, this is called one hop. And so an HF frequency can propagate all the way around the Earth by multiple hops using the ionosphere. But that is skywave propagation. If I go back for a minute to ground wave propagation, when that works, as an example, we have set up a station in the Williamsburg area on 40 meters. That's 7 megahertz. And there's another station down in Suffolk. This is a friend of ours named Kenzie. Kenzie was transmitting down from Suffolk. I could barely hear her on 40 meters on 7 megahertz because the ground wave just didn't make it far enough up to, barely made it all the way up to Williamsburg. So she was fading in and out, and it was a real rough copy on her. But that was because the ground wave propagation just wasn't quite doing it. Meanwhile, what we'll get into here in a little bit, I couldn't hear her, but up and down the East Coast, whoa, she was getting a lot of traffic. A lot of people like talking to YLs. She's a nice lady to talk to, so she was getting a lot of stations wanting to contact her. They were hearing her just fine because they were talking to her by the skywave. That made it much easier. So I was kind of like in this skip zone area. I couldn't hear that well. Line of sight, radio energy travels in a straight line from a transmitting antenna to a receiving antenna, also called a straight direct path. There is some attenuation to the signal as the radio wave travels due to spreading out. That inverse square law you might have learned about in physics. But this is the primary propagation mode for UHF and VHF signals. So that's why this is important for you guys. The radio waves can be reflected by anything in the path on the way there, and it'll reflect in a number of ways. Some of it can be a building, a hill, weather-related changes in the atmosphere, and as I mentioned earlier, even vegetation can absorb VHF, UHF radio waves. So there's quite a bit of difference between operating in the wintertime as opposed to in the summertime. You will notice in the wintertime, you get clearer reception. As your ear gets used to all of this, in the beginning, it may not sound like much difference, but as you all get into this, you will notice that there's a difference. Or as you get further away from a repeater, it's harder in the summertime to hit it, but in the wintertime, you might not have as much trouble hearing it. And precipitation like we're having today, fog, rain, this can absorb UHF, VHF, and microwave signals quite a bit. And again, you might need to be on the edge to really notice that difference, but it's actually there. If you're close enough, you got a powerful enough transmitter or a sensitive enough receiver, or hopefully both, you may not notice this difference as much, but it's actually happening. So for, as an example here, line of sight. At this particular height, whatever that height is, to the horizon is 25 miles. And so equally, if there's a receiver over here at this end, same height, it will be 25 miles past the horizon on the other side. That's 50 miles, and maybe you're just barely going to make it, since it's just barely coming over the top of the horizon there in between the transmit and the receive sites. If you put a repeater right there in the middle, wow, that will improve reception 100%. And as a repeater, did that get explained to you? You all understand the concept of a repeater? Whatever it hears coming in on one frequency, it just turns right around and retransmits it on a separate frequency.
Can the repeater be propagating differently?
Line
of sight, and then the repeater is doing something else, and you still get that signal?
It could be. I mean, because anything, even whether it's something in the line of sight of a repeater or the radio itself, it's going to be the same kind of effect, yes. For example, there could be a big tall mountain right over here.
Yeah.
So the ideal thing is to have the repeater up on top of the house.
Yeah.
But that can't be the case all the time. So yeah, that mountain would cause a problem. And there are some ways to get around this. I'll talk about it in a minute, because the slides are going on a different way here. But when we talk about knife edge propagation and reflection and things like that, we'll see how that can make a difference, but for the good. Okay, ground wave. So now this is where HF frequencies goes across the ground around the curvature of the Earth for a limited distance. At lower HF frequencies, these radio waves can follow the Earth's surface as they travel. So it's a great way. We might be able to, well, as that earlier example of mine from here in Matthews, you might be able to get to Williamsburg, depending on the frequency band. You might be able to get all the way to Richmond. Yeah, you might, if you look north and south, you might be able to get up to Northern Virginia on a ground wave, again, depending on the band. So because it's following the curvature of the Earth for a bit, it goes beyond the range of line of sight. It can be a couple of 100 miles on some bands that we use. And that's skywave. So now we're back into the HF thing. Propagation of radio waves reflected or refracted back towards Earth from the ionosphere. I'm going to make a quick distinction between reflection and refraction. Anybody want to hazard a guess? Or anybody remember it from physics? Yeah, go ahead.
On here, but reflect would be it would actually bounce in the same, basically same trajectory kind of, and refracted would be you hit it and then it goes a different angle.
Yes, I'll accept that.
Yeah.
It bends instead of reflects.
Yeah.
Okay, so the waves get reflected, diffracted, or refracted. And we'll get into that here in a minute. So this is exactly what you were talking about. A reflection is an exact mirror image, as it were. Refraction, it bends a little bit because the speed changes. And radio waves are traveling at the speed of light. And I think there's a slide coming up here that'll show the things that we all learned in high school physics or elementary school. I don't know if they teach physics in elementary school. And then diffraction, the waves go off in all sorts of different directions because of many different reasons. So with reflections, it can be reflected, a radio wave can be reflected by any conductive surface or any sudden change in the media through which it travels. So the ground can reflect a radio wave. Water is a great reflector of radio waves. Buildings will do it, even the moon. And if we haven't alluded to this before, but radio sport, I guess if you want to call it, or a real challenge that as a technician, you can get into this because it's done at the higher frequencies, but EME, Earth, Moon bounce. If you accomplish a QSO or a contact via moon bounce, that is a tremendous achievement. Congratulations if you were able to achieve that.
Sorry. I guess
No,
I have a lot of
go
questions
right
today.
ahead.
But, or talking today, I guess you say. So if you have your transmit, so if you're getting a better signal as direct, can you do something to not reflect?
Yes,
Okay, so you can then, instead of, anyway, you get a better signal this way, but you also can do this way, but you can aim it to go direct and not reflect.
yes, yes. And I'll get into a couple of examples of that coming up. So keep that in mind. And if it doesn't answer your question, let me know. That means I missed a slide.
No worries.
All right. Refraction. So here's the picture. This was back in elementary physics. Just putting the spoon in that glass of water. The light, as it comes through that water, changes speed, and that makes it change direction slightly as it goes through a different medium. So that's why it doesn't quite match up. The line of sight, the light wave reflecting off that spoon is changing, going through a different medium, so the speed is changing. Same thing for radio wave. Here, refraction. So it allows the signals to bend back. This refracting takes place up in the ionosphere. We're going to touch on it a little bit here because as technicians, you will have privileges, even with sideband voice, to talk on the 10-meter band and the 28 megahertz range, way up at the top of the HF scale. You don't get that privilege at the lower HF frequencies, but you do at 10 meters, so we touch on it here. When you get to general, we're going to study a lot more about ionospheric conditions and refraction that takes place up in the ionosphere. Anyway, when you transmit from the transmitter site, it's I know when we depict this in these kind of illustrations, it's always depicted as a straight line, but when a transmitter or when an antenna transmits, it's spreading out from that antenna point in all directions, or in many different directions. Just a single signal here, some of that is going almost straight up, hits into the ionosphere up here at this layer, bends around a little bit and turns off and continues straight on into space. So the energy from that transmitter site is being wasted. But on that same signal, there's some of that signal is going straight up into a little bit further off into the ionosphere, hits this particular layer, and starts to bend back down. And it comes down here to the other side of the horizon to the receiver site down there. And the same might happen at a lower angle. It now hits lower in the ionosphere, but as long as that part of the ionosphere is still refracting those signals, it will also bend, and part of that energy will come down here to that transmitter or to that receiver site. It comes up in a different picture, but you can imagine too, one of these signals will refract off of here and go off into this direction and completely miss the horizon and the Earth altogether. So again, that's wasted energy. Instead of going straight up into space, it's going off to the side of the Earth and being lost out there. But some of this signal in between will hit that receiver. So that's why when you're trying to listen to shortwave, oh gosh, sometimes you can barely hear, you get some static. All of a sudden, sometimes it comes in really clear. It's because of the ionosphere is not smooth, so it's kind of like waves up there. So sometimes it's coming down pretty good, reflecting and refracting down, and other times, a second later, that wave has changed up there, and it's gone off into space or one way or the other. Diffraction. This is more directed at UHF, VHF, and above. The signal source radiates out. It hits something, some kind of a barrier. Usually it's a building. And what it does is, because of the diffraction on the opposite side there, some of those radio waves are diffracting, splitting up, and some of them are being absorbed and not transmitting at all. And so you're in a skip zone, as it were. They call it the shadow zone, where the diffraction signals are. I can't read that bottom part. The signal appears in the shadow zone. Okay. So with this knife edge propagation, that will happen at the VHF frequencies. So for example, I might not hear the Gloucester repeater sitting right here. But I swear, if I take a step over here, now it comes in loud and clear. And maybe if I take another step or two, now it's disappeared. And you will hear us talking on, I know this has happened on our repeater quite a bit. Someone's coming in, they're talking on an HT, and usually it's a new technician. Not always though, I'm very guilty of this. But they're trying to get into the repeater for one of our nets. Boy, they're coming in really, really rough. And it's like, Jim, take 2 steps to the side. And as long as, and Jim doesn't know this, if the repeater is over here and you're moving perpendicular to it, yes, being over here, suddenly he's clears the bell. Jim, get yourself a spray can, mark an X right there on your floor. That's where you want to stand when you want to talk into the repeater, because when you're back over here, no good. But the fact that you're perpendicular, moving perpendicular to the repeater makes a big difference, because if I'm not receiving it here, I can take 2 steps backward or 2 steps forward, and I'm still in that skip zone of that diffraction shadow, and it's not going to work. So sometimes it really helps wherever you're transmitting for, especially if you're going into a repeater, or even if it's not a repeater, if you're simplex talking to somebody over there, simplex, just one-on-one, same frequency. Knowing where that person is or the general direction is going to make a difference as to whether or not you want to go this way or you want to go this way. Propagation properties. Range is slightly greater than visual line of sight due to gradual refraction, creating the radio horizon. And so when I had mentioned earlier, that VHF, UHF, and above is line of sight. This is true. But there is a little bit of refraction going on, so it will go, your VHF, UHF signal will go a little bit beyond the horizon. Not very far, but a little bit that it's not line of sight. And I can guarantee you reception is going to be really raggedy when you're in that area beyond line of sight. And you will be right on the edge of dropping out. But it does happen. UHF signals penetrate buildings better than HF and VHF because of the shorter wavelength. So this is also one of the reasons public services have moved out of the 400 megahertz area up into 800 and above, because radio signals will get out of the building better. But there's some other trade-offs that I don't think we need to worry about. But the higher up in the frequencies you're going, power, how powerful, how many watts you're putting out becomes more critical. But it also means we're getting up into the microwave area. Microwaves into the body are a bad thing. So when you start getting up into the higher frequencies, more power is actually a bad thing if that transmitting antenna is right near you.
So higher frequencies are easier to go through the building, but they can't curvature the earth. Right?
No,
So
no, not as well as it will be as you
for
go down
low
low.
frequency.
VHF a little bit, but definitely when you get down into H. Buildings themselves may block line of sight, but reflected and diffracted waves can get around these obstructions. So that also goes back to your questions. And here's an illustration to your point. So it hits the top of that mountain and diffracts, comes down in the shadow side, the radio shadow side of the mountain. So, some places you're going to get that transmitter better, like at the front door here, than you will over here in this room off to the right. The rest of the energy, hits that mountain, it gets absorbed, but it might also reflect off the mountain down into this area, but it will also be reflecting up into space. And this other transmission line just goes over the top of the mountain point peak and keeps on going. So you're not receiving that radio energy either.
And also for picket fencing, you'll hear a lot of mobile radios do that. So if you're in your car transmitting, if I'm talking to Kerry, he might say, "Alan, you have a lot of picket fencing." That's because I'm moving. Once I become stationary or stopped, then it will stop.
Because now you're standing right here where I put that X in a sense, but you're on the road. But when the car starts moving, it passes through all of these null areas. So you'll notice it on talking to people. Their signal comes in, it drops out, it comes in, it drops out, it comes in, like passing a picket fence. Other multipath propagation. So this is a more complex depiction of what we're all talking about, where everything combined together, particularly in an urban area. Radio signal will bounce off of buildings, not just one, but more than one. And there might even be a mountain or a hill in the way. You might have leaves and vegetation, things like that. And, we don't get into the discussion here so much. But airplanes, signals will bounce off of airplanes as they're flying overhead. So if you're particularly in a heavily traveled corridor, you can get a lot of this kind of multi-path propagation as well, signals bouncing off the planes. So you'll be hearing picket fencing, and it might go a lot quicker and faster, because even though it might be diffracting off of this building over here and you're in a null area, this building over here, you happen to be in the reflected area. So you may not recognize the picket fencing, or it may not be as bad because one is compensating for what's happening with the other building. A couple of practice questions. I'm going to go through these really, really fast because I'm already half an hour into this and we're not very far along. Why do VHF signal strength sometimes vary greatly when the antenna is moved just a few feet, as we were talking about? C? I'll go along with that very well, thank you. What is the effect of vegetation on UHF and microwave signals? The higher up you go, what's happening? Knife edge, absorption, amplification, polarization. What are the two dumb answers? C and D, amplification. Nothing, I can tell you, there is nothing in the environment that's going to amplify your signal unless it's an amplifier. Polarization, rotation. Boy, they love to throw in stupid answers relating basically to satellite communication. So D doesn't work. And here in the technician course, even though as a technician, you will be able to talk to satellites if you want. But as a condition for getting a technician license, you don't need to know a lot about that. So we don't discuss it so much. But D is out. So that means we're talking absorption or knife edge diffraction.
B.
B it is. What's meant by the term picket fencing? Alternating transmissions during a net operation. Net operation's got nothing to do with it. Rapid flutter on mobile signals due to multipath. Oh, that sounds good. Type of ground system used with vertical antennas. No, we haven't even discussed that. Local versus long distance communication. Not sure what they mean by that either. So B is your answer. What weather condition might decrease the range at microwave frequencies? Look outside. That's your answer. What is a likely cause of irregular fading of signals propagated by the ionosphere? A likely cause of irregular fading, meaning it's coming in, it's going out, it's coming in. So frequency shift due to Faraday rotation. Okay, this goes back to what I'm talking about. They keep coming up with these answers related to satellite operation, and we're not covering that at all. So that's dumb answer number one. Interference from thunderstorms? I don't know, but thunderstorms don't even come close to the ionosphere. So there's dumb answer number two. Intermodulation, distortion. Oh, now that's an interesting discussion to have, but that doesn't answer the answer to the question here. So D is the random combining of signals arriving via different paths. So we saw in that earlier illustration, the one signal was going straight into space, or at least diffracted to go into space. One was bouncing off and coming back down. Another one was bouncing off lower in the ionosphere, but coming down. But the one is traveling a further distance. So it arrives at a slightly different time than the other one. Now that time, we are talking about a microsecond. But sometimes, it's not a clear voice you're hearing. It's a little buzzy or fuzzy or something like that. And the reason is one radio signal is arriving just a fraction of a microsecond ahead of the other. What effect does multipath propagation have on data transmissions? All right, now this didn't get covered, but it's possible this will come up in the test. Transmission rates must be increased by a factor equal to the number of separate paths observed. Well, I'm sorry, but I can tell you right off the bat, that's a dumb answer because I can't observe the paths. I do not see radio waves. So there is nothing to observe. Transmission rates must be decreased by a factor for the same reason here. Separate paths are being observed. I am not observing anything. No significant changes will occur if the signals are transmitted using FM. And we didn't talk about that, but error rates are likely to increase because of the confusion that might be interpreted at the receiving end, because the signals are coming in at a slightly different data rates. So your answer when you get to this one, I'm telling you just, A, you can eliminate these two because you cannot observe. But the answer is D here. The rates are likely to increase, meaning your transmission message will likely not get decoded, or it'll have holes in it. What's the effect of fog and rain on signals in the 10 meter and 6 meter bands? Both of these are technician bands that you're going to have privileges on. What's the effect of fog and rain since we got a foggy and rainy day out there? Absorption, little effect, deflection, or a range increase? It's not going to be little effect, it's going to be absorption. Oh, little effect. What? Hang on a minute. What? What's the effect of fog and rain on signals?
And I was gonna say,
Well, it's because we're not getting up into the UHF, VHF, and above. We're actually moving down towards HF. Okay, this one fooled me. Go with what this answer says, not what Carrie said. Okay, which of the following effects may allow radio signals to travel beyond obstructions between the transmitting and receiving stations? This goes back to your question directly. Which one of these may allow it? Knife edge diffraction. Here we get Faraday rotation yet again. Oh, and I love this one, quantum tunneling. Isn't that great? Doesn't that, bring the sci-fi out in you? Or a Doppler shift, which again goes back to satellites. So those are the two dumb ones, Faraday rotation. Well, I'm not got as much as I really like this answer. Quantum tunneling, I have no idea what that is. And Doppler shift. So the answer is knife edge diffraction. Okay, why is the radio horizon for UHF, VHF more distant than the visual horizon? So it's hitting that visual horizon and slightly going beyond to the radio horizon. Radio signals move somewhat faster than the speed of light. Okay, dumb answer. We know nothing travels faster than the speed of light, at least in today's science. Tomorrow might be different. Radio waves are not blocked by dust particles. The atmosphere refracts radio waves slightly. Radio waves are blocked by dust particles. So dust particles got nothing to do with this. So your atmosphere refracts radio waves slightly is the right answer. All right, let's take a break. It's been 45 minutes. So grab another cup of coffee or get rid of the cup of coffee you already had.
I think I figured it out too.